Um, the idea of inverse trig, in a very watered down way of talking about it, is if I were to hand you this question right here, and I said that we took the sine of something and we got an answer of 1/2, what was that something? Okay, that's kind of where we're going to go with this chapter. Today we're going to look at the graphs of these functions, but like if you're a hand trick person, it's really pretty easy to find your inverse sine, because if I want 1/2, I would do this, and my answer would be a pi/6 angle. Okay, well, what I have covered up here is, yeah, that's kind of the idea of inverse trig. It's undoing the sine function. It's finding the angle itself, getting that by itself. But there are some restrictions to it, which we're going to see a little bit in our graphing today. The graphing kind of explains why there's the restrictions. Tomorrow we'll care more about what the restrictions are as we go to find our values of inverse trig. But that's kind of the idea of it. Inverse trig has 3 different ways of asking you to do the inverse of that function. Now, first of all, we will only do inverse trig for sine, cosine, and tangent. We will not look at secant, cosecant, or cotangent. So just your basic 3. Up here, it's listed 3 different ways. The word inverse, literally sitting in front of sine. The notation we used first semester, which is raised to the -1. Or this thing that's called arc sine. Guys, that's all the exact same question. Why there has to be 3 different notations for the same thing, I don't know. But they are all the same. Okay? Do not be confused. They are not different questions. They are completely interchangeable to each other. Okay? First semester, we did spend some time talking about what type of functions have inverses. And we used this thing called the horizontal line test. And we drew a horizontal line through our graph. And if it hit our graph in more than one place, it actually didn't have an inverse. And we said that that graph would not have, or that function would not have an inverse function. Sine fails that horizontal line test. Cosine fails it. Tangent fails it. They all fail it, which is why it's going to take a little bit of manipulation to actually have an inverse. The other idea behind inverses, first semester, okay, we did this horizontal line test. We said, yeah, it has an inverse. How do I find it? We took all of our x's and we took all of our y's and we flip-flopped them. If you guys remember, in the ordered pair, we would literally just flip the 2 numbers. In an equation, we'd make all the x's y's and all the y's x's and solve for y. Okay? Well, it's the same idea. If this was my normal ordered pair to draw a sine curve, to get its inverse, I flip-flop the x's and y's. But the weird part about doing that is if I flip-flop my x's and y's, remember the weird way we number our x-axis when we draw a sine curve? Well, now that weird way has to be up our y-axis instead. So what you're going to notice is as I'm graphing these flip-flopped x's and y's to get this inverse, is that now I label my y-axis the way I used to label my x-axis. So 2 pi and pi, 1 and -1, right? And as I were to graph these ordered pairs, I would have the point 0, 0, 1 pi over 2, 0 pi, just going down this list here, -1, 3 pi over 2, and 0, 2 pi. And if you kind of turn your head to the side, you can see that sine curve. Right? See that pattern starting? And we know that a sine curve just continues that pattern. I just have a few example points here, but if we were to continue that pattern here, it would just keep going to our midline, which is our y-axis now, and we would see this going on. Clearly fails our vertical line test. It is not a function. But in order to use it, we need it to be a function, and so that's where the restriction comes into play. The restriction on a sine curve needs to account for everything, positive and negative values. So on the first one, I'll just show you directly what it is. It happens right here from -pi/2 up to pi/2. And this little curve in here has both negative values and positive values, which represents all values on the unit circle. And so this little green box that I have here, you're going to see blown up on the next page, and that's where that little curve is. And that's why they're curves, because it really is part of your sine curve that we were drawing. There it is blown up into a bigger picture. From -pi/2 up to pi/2, from -1 over to 1, that little curve that I highlighted would be what a inverse sine curve is restricted to, so that it is a function. When we talk about functions, we talk about all its properties, domain and range. Domain, the farthest left, it hits at this point. So the farthest left that it would go is -1. The farthest right would be this point right here, would be over at 1. Lowest point, again, it hits at this point, so the lowest point would be -pi/2. highest point it hits at is pi over 2. This is highlighted in this picture. From negative pi over 2 to pi over 2 would be this red line right here, which spans quadrant 4 and quadrant 1. What it's saying is inverse sine is defined in quadrants 1 and quadrant 4. That it becomes very important to us tomorrow. Doesn't impact what we do today at all, but that's going to be our major topic tomorrow, is which quadrants it's defined in. And just a reminder that this can be written in any of these three ways: inverse sine, sine raised to the negative 1, or arc sine, all the exact same thing. Okay? Question so far. Same idea for cosine and tangent, is we're going to look at where it needs to be restricted. Obviously fails our vertical line test, so we restrict it. We do the same idea again as we flip-flop our x's and y's to get this picture started. We number our y-axis just like we used to number our x-axis. Everything turns on its side as we exchange our x's and y's, but the points end up in a slightly different place. 1, 0 would be here. 0, pi over 2, negative 1 pi, 0, 3 pi over 2, and 1, 2 pi starts that cosine curve on its side. And obviously we know that with all of these curves, they just continue their pattern. So if I were to continue this pattern all the way down, I would go back to my midline, which is the y-axis, below, midline above, all turned on its side here. The problem with the restriction is it doesn't work the same for both functions. If I were to just look at the same little restriction that we looked at on our sine curve, which was from pi over 2, negative pi over 2 up to pi over 2, do you see that that little blue curve is not a function still, because it still fails your vertical line test, and actually it only represents the positive values? So that restriction doesn't work for cosine, which is why they have a different restriction. This gets slid up a little bit here. This window right here shows negative and positive. It passes my vertical line test, so as we zoom in on a tiny little portion of the inverse cosine curve, that's the portion you're looking at. Okay, so as I switch the page here, there it is blown up into a bigger picture. As we've got the negative values, we've got the positive values. Domain's going to look the same. The farthest left that goes is negative 1. Farthest right is 1. That was the range of a sine or a cosine graph, right? The range, then for this, lowest point it hits is 0, highest point it hits is pi. This difference right here, which is represented here from 0 to pi, again, going to be a very important difference between inverse sine versus inverse cosine. Okay, we'll spend more time talking about that tomorrow. Cosine, inverse cosine is defined in quadrants 1 and 2. Don't forget, all of those mean the exact same thing. Okay. The last one, which is a little bit unique, is the tangent one. Obviously, its graph looks very different than sine and cosine, so as we do the inverse, it's also going to look very different. The whole flipping of the x's and y's thing doesn't work as well for this one because we've got these undefineds, which were our vertical asymptotes. So as I switch them, it doesn't really make sense to have a point undefined, comma, 3 pi over 2. We'll talk about what that looks like over here. Same thing, though, everything gets flipped. We do still have a couple points on here, 0, 0, 0 pi, 0, 2 pi, so here, here, and here. And these undefineds represented a vertical asymptote. Okay, well, if x's and y's flip, vertical lines flip to horizontal lines. So now it's a horizontal line up at pi over 2 instead of a vertical line over at pi over 2. So it becomes a horizontal asymptote instead of a vertical asymptote. Okay, and there you start seeing the dot on our midline, exactly halfway between our asymptotes. And so what happens is our graph will fill in there. It continues to increase between our asymptotes, so I'd go over to 1 up to pi over 4, down to negative pi over 4. It increases between our asymptotes, and all of them would increase between your asymptotes. Still not a function, right? If I were to draw a vertical line, I would hit the graph at, like, well, in my picture 3 times, but infinitely many times. And so we restrict, and its restriction matches the same as sine. I can look at just negative pi over 2 to pi over 2, and that would give me a picture of everything inverse tangent. And that's what is zoomed in on here for your inverse tangent function. Domain and range are very different on tangent than it is compared to sine and cosine because, again, we've got arrows on this one, which we did not before. Well, arrows means it continues. The arrow pointing to the left means it continues to the left forever. So the domain on this is actually unrestricted. Continues to the left forever, continues to the right forever. No restrictions on the domain of an inverse tangent. The range, however, is restricted. Okay, lowest point to highest point. Well, it's going to get down to close to this asymptote. Is it ever going to hit that asymptote? No. How do I show that when I write it on the board? Yeah, parentheses, right? We use a parentheses to show that it gets close to that number but does not actually get there. Same thing going up to the upper horizontal asymptote. It gets close to but never actually gets to pi over 2 at the top. Now, again, save this conversation for tomorrow, but notice that's represented then as an open dot. Gets close to but doesn't actually get to negative pi over 2 and pi over 2. It's defined in the same two quadrants as sine, but doesn't actually equal pi over 2 at the ends. Okay, same notation, it doesn't matter. And what you'll notice on your worksheet is it kind of flips through all three of those options just to continue to show you that it can be written any way, and it's asking you to do the exact same thing every time. So, as with every other function we've been handed, our book does summarize that. So this is what it looked like in your book, everything we just kind of talked through. But what does it mean when I graph it? Guys, I think that graphing inverse sine, cosine, and tangent is way easier if you attack it like you did functions first semester. Know your favorite points and apply your transformations just like you would have. So let's talk about what are our favorite points for each of these. You have three favorite points for each of those graphs. Somehow, some way, you're going to have to remember what those are. Practice, etc. Know these 3 points. So for our inverse sine graph, the way I would draw my graph to start with, first of all, on my x-axis, I would number from -1 to 1. On my y-axis, I would go up to pi over 2 and down to negative pi over 2. My favorite points are this. In the order that you write them in your table, pick whatever makes sense to you. It doesn't matter to me. I kind of work from right to left. 1 pi over 2 is one of our ordered pairs. It goes through the origin 0, 0. And -1, negative pi over 2. And this part is very important as you understand where these points are coming from. These came from a sine curve. Curve is in the word, right? You cannot connect these points with a straight line. It's not supposed to be a straight line. It's part of a sine curve, right? So this was kind of like the top of a hill of a sine curve. So I'd curve up this way. This was the bottom of a valley, curve down that way, always curving away from your y-axis, but make sure that you connect the dots with a curve. All right, so doing the same thing for our cosine curve. How do I start drawing that? Again, on my x-axis, I would go from -1 to 1. On my y-axis, I would go from 0, have a tick mark that represents pi over 2, and then a tick mark that represents pi. Your favorite points would be at 1, 0, 0, pi over 2, and -1, pi. And again, we are looking at the sideways curve of a cosine. So you need to curve away from your y-axis. This would have been the bottom of a valley, and that would have been the top of a hill, right? So curving away to form those valleys and hills. And our tangent, now the hard part about tangent is you have to remember both the favorite points and you keep in mind the asymptotes that go along with it, which don't show up in your table. Start by drawing your picture the same way you would for a sine curve, as we're up at pi over 2 and down at negative pi over 2 for our y-axis. For our x-axis, -1 to 1. Your favorite points on a tangent curve would be at 0, 0. And then we go over 1 up halfway to the asymptote. And your asymptote's not going to show up on your table, but should be drawn up there at pi over 2. You have to have an asymptote. And down at negative pi over 2. So we go right to 1 up halfway. Well, halfway is actually the point pi over 4. And then left halfway, or left to 1 down halfway, which would be -1, negative pi over 4. Should have arrows at the end of this to show that it does continue. Okay, some major differences and some notes to make about all of this. These two graphs end at the end dots. They do not extend past. No arrows. This one has arrows, right? So that is a major difference between those graphs. But the other thing is you do have asymptotes on this one. Your asymptote, which is your horizontal asymptotes, will move if one of two things happens. You have a vertical shift. If you think about your equation with letter D, right? Or you have a vertical stretch or shrink, which was an A, an amplitude in our trig equations, that our asymptote will do the same thing. Now, it's not in my table, so I kind of have to think about that off to the side, but it will get impacted by anything vertical happening to my graph as well. This page right here sums up this whole section. You got to know those points. You got to know those graph shapes. Any questions? Okay. So I would suggest that you, even though your equations are going to look like the equations I handed you yesterday on your test, that I would treat them like the equations you saw first semester. That if you have a multiplication on the outside, which would be A, that you go to your table, and remember multiplication on the outside impacted which column? Outside. Y. Anything outside is going to impact our graph vertically, right? And that I just take this number and I multiply my Y column of my table of favorite points by whatever A is. Same thing if I have a B, is I would treat it just like I would. So multiplication on the inside would be considered a horizontal shrink or stretch, opposite of what we see. Inside things impact our X column. So I would take my table of favorite points, I would go to my X column and multiply by reciprocal, right? 1 over B. Reciprocal because it does opposite of what we think it should. That if it is a C or a D, I'm going to just count. And you have to be very careful on D because almost always your numbering will not match. So be careful about the units. Why do I say that about D? Because typically it will tell you to move up 2, but your y-axis is now measured in radians. Okay, so as we look at our y-axis measured in radians, for example, pi and pi over 2, we want to think of what those are approximately. Pi is approximately 3 or a little bit more, right? So if pi is approximately 3, pi over 2 is approximately 1.5. Right? So if I was told to move this dot up 2, I got to move a little past that tick mark. Not 2 tick marks, but a little past the one that's about 1.5, right? So it's going to be a lot of approximation when you're doing a vertical shift. The other thing is, remember that a vertical shift will also move your horizontal asymptote, right? And amplitude will also change your vertical horizontal asymptote. We will take A times, now your asymptote is at pi over 2, so A times pi over 2 to move the horizontal asymptote on an inverse tangent graph. Okay, so whatever you multiplied your y column by, you need to multiply pi over 2 by that same number to figure out where your asymptotes would be. Your goal by the end of the worksheet today is that you know your table of favorite points, that we practice it enough times that we know those favorite points, because again, that's kind of an expectation that we can do those. All right, I have very basic examples here to end us with. First one, y equals inverse sine of 2x. We want to identify for ourselves our table of favorite points, which eventually we are going to know by heart. Our inverse sine points would be at 1, comma, pi over 2, 0, 0, -1, negative pi over 2. However you're going to go about memorizing those, know those points. What is the transformation we see happening in this equation? Horizontal. Yeah. Yep, horizontal. And we have to think opposite, right? Horizontal shrink would be the probably vocab words that we would pick for that. So horizontal things impact my x column. We would come to our x column, multiply by its reciprocal. So I'm going to go down my x column and multiply by a half. Times 1 is a half, times 0 is 0, times -1 is negative a half. And I would graph that. Okay, now I can go ahead and just number my x-axis to match that if I want to, or if I want to leave it as 1 and -1. Then I need to make sure I only go over a half up to pi, 0, 0, negative a half, negative pi, and you have to curve away from your y-axis. So curve away from my y-axis, away from my y-axis. Should not extend past the dots, should not have arrows. Questions? Okay. Like I said, I've got one basic example of each one here. I'm going to get rid of that. Inverse cosine of x minus 3. Where that -3 is located, which direction is it moving our graph? Is it inside or outside? I feel like you're giving me all options. So your options are right, left, up, or down. That's outside, isn't it? That should be down 3. Yeah. It's been a while since we've graphed not thinking trig, right? And we're not really thinking trig on this. We're thinking normal transformations. I'm going to take my favorite points, put them out there, and move them down 3. So my favorite points for a cosine curve, which again we're going to practice and get memorized at some point, are 1, 0, and -1. And it goes 1, 0, pi over 2, and pi. I'm going to make this graph really big to kind of exaggerate here for effect. But this is a great example of how the numbering does not play nicely with vertical shifts very often. Okay. So my normal points on this graph would be at 1, 0. This is not my end result here. I'm just showing you where these would start. 0, pi over 2. And -1 pi. Okay, but my transformation says those are supposed to move down 3. And this is kind of what we talked about at the beginning, is I want to pay attention to what did these marks really represent. Well, this is approximately, actually a little bit more than 3, right? 3.14 or something, whatever pi is. Okay, and this would be approximately half of that, approximately 1.5. Well, if I'm supposed to move 3, this dot is up at 3.14. To move 3, I'd move almost all the way down to the x-axis, right? If I got to the x-axis, it'd be 3.14, so I'm going to move almost all the way there. So that was a distance of almost 2 tick marks, which means I move every dot almost 2 tick marks. That's 1.5. That's almost 3.14. That would be about 1.5, almost 3.14, curve away from my y-axis. That's the challenge in your vertical shifts, is it's going to be approximate. Use approximately 1.5 and approximately 3 to help you with estimating distances. Now, not all transformations on a tangent graph will impact your horizontal asymptotes, so we do have to pay attention to, does this particular transformation impact those? Now, let's try this one more time. What, thank you. That one would be moving us left 1, yes? Inside, because of the parentheses, and we think opposite. So it's going to take my graph and move it left 1. Our normal graph would go pi over 2 down to negative pi over 2, negative 1 to 1, and it would have horizontal asymptotes running here and down here, okay? And if I take a horizontal line and I slide it to the left, isn't it still the same exact horizontal line, right? So horizontal changes do not impact horizontal asymptotes because all it's doing is taking that same line and shifting it, which is the exact same horizontal line, okay? So you'll notice that my asymptotes don't move. My 3 points that I put on a tangent curve, which are at 0, 0, 1 pi over 4, and negative 1, negative pi over 4, each are going to shift to the left 1. So normally I'd be over at 1 up pi over 4, shift that to the left 1, 0, 0, shifted to the left 1, negative 1, negative pi over 4, shifted to the left 1, but it's the same looking graph with arrows. Questions? All right. Your assignment tonight, don't forget vertical things are going to impact the pi over 2 location of your asymptotes. Don't forget about the asymptotes. Apply those transformations to those as well.